So here's a better proof, and it's going to work for all values of theta, not just this handy triangle, but I think the handy triangle is really good to remember, okay? I'm going to come back to these guys. These double angle formulas are how I got the t results in the first place, how I got these two algebraic expressions for tan. So I'm going to use the same for sine, right, and for cosine. So let's do sine first. If I replace, just like I did before, all the thetas with half thetas, okay, I'm going to get, on the left-hand side, 2 times half theta, which is just theta. And then I'm going to get 2 sine half theta, cos half theta. No big deal. Okay, now, excuse me. I need to get this all in terms of tans. I need to get it all in terms of tans because that's what t is, right? So in order to get rid of any sines and cosines and just have t's flying around, I've got to turn these guys into tans. So how do I do it? My first step is I'm going to divide by 1, but instead of 1, I'm going to use the Pythagorean identity, which is cos squared plus sine squared. Okay? Of course, I could write cos squared theta and sine squared theta, but I have everything else in terms of theta on 2. So everything here is in terms of the same angle, which is why the functions can relate to each other. All right? Okay, now remember, bless you, where I'm headed. This is where I'm going, okay? So I'm going to do one operation to take me from here to there. Remember what these are? Remember what these t's are? They're tan half thetas, right? Tan half thetas. So how do I get tan half thetas appearing here? What am I going to do? Think back to when we had equations in terms of sines and cosines, right? And what we did in order to get things in terms of tan, right? I'm going to need to divide. What shall I divide by? I'm going to divide the top and the bottom, right? Think about the top. If I divided the top by cos, then that cos would disappear, right? If I divide by cos again, then this sign will turn into a tan, right? So I'll do cos squared, right? Now if you divide the top, you better divide the bottom as well. Okay, and now you can see what's going to happen, right? What's going to appear on the top? 2 tan theta on 2, which is exactly what I want. Okay. And then what happens here on the denominator? Well, this guy is going to turn to 1. And then this guy is going to turn into sine squared on cos squared, which is tan squared. Okay, like that. So there's the tan half thetas that I'm after. That's 2t on 1 plus t squared. Okay, see how it worked? So this is a more thorough way of doing it. You see, I didn't introduce any triangles to prove this. I just used identities which I know, which are always true. Okay, but it's kind of like, why did you do that? Like, why did I divide by this? Because I wanted to. And why did I divide by this? Because I knew where I was headed already, right? So I think this is generally a better way to remember it, but this is a better way to prove it. Okay? Really quickly, and now that I've shown you how I did it with sine, you can help me do a lot faster with cosine. What do you think my first step should be?
Change everything to...
Yeah, good. I'll change everything in terms of thetas on 2's on here and thetas here. So I'll divide all the thetas by 2, in other words. So I'll have this. Okay. Remember, I want to get things in terms of tans, right? So what trick did I employ? Here, on my first line with sine.
Divide by 1.
I divided by 1, but I'll divide by 1 in a helpful way rather than a boring way. So that's kind of helpful, right? And then what did I do next?
Divide by cos.
Yeah, I'm going to turn all of these cos squareds into 1s and all the sine squareds into tan squared. Divide by cos squared on cos squared. Okay, and you can see it literally just falls out in exactly the same way that sine does, right? I'm going to get 1 minus and 1 plus. Okay, so, excuse me, this is a great little result. This is the proper proof. But I'm going to recommend, just like, you know, one of the first things you might do when you sit down and you start doing a paper which has any kind of trick involved in it, you might draw one of these, right? Sorry, that's not what I want. I want 30, 60, 90, right? And you think, okay, exact values, I know that sine 30 is a half, and that makes this side root 3, okay? Just like that's a useful tool for remembering your exact values, this is a useful tool for remembering all of the t results in the right order, because you can just read sine, cos, and tan off of them. Yep.
I don't really get the dividing by 1 thing.
Okay, so we'll go to sine because that's the first time I did it. I started with this, right? But I wanted to turn all of these sines and cosines into tans, okay? And I knew that I was going to have a 1 plus tan squared on the denominator, okay? But I don't even have a denominator here, okay? So I kind of knew in advance I'd need to introduce one, but I can't just introduce, like, I'm going to divide by 3 or 4 or 5, because that would actually change this. So I divided by 1 because dividing by 1 doesn't change things, right? So dividing by 1, it's still the same identity, right? I haven't changed its value. But having introduced these, it gives me a kind of bridge to get to this in a helpful way, okay?